In this presentation on real numbers, we are going to talk about Euclid's division lemma. So the first term we come across over here, it is this term lemma. So lemma is just a proven statement that is used to prove another statement. So we are saying when we are talking about Euclid's division lemma, it is a statement that is already proven, and this Euclid's division lemma, it will be used to prove some other results. So first of all, we look at the statement of Euclid's division lemma. So we are saying that for any two given positive integers a and b, suppose I am talking about the integers 117 and another integer I am considering it is 4. We have there exist unique whole numbers q and r such that a is equal to bq plus r. So how we are going to calculate these two numbers q and r? We are saying that if we divide 117 by 14, what we get is, we get 4 to the 8. On subtracting this value, we are getting the remainder as 3. Then we have 4 9s are 36. The remainder we are left over here, it is 1. So these two numbers q and r, we are saying in this case these two numbers, they are 29, this number 29 that we have obtained, and this number 1 that we have obtained. Now it is interesting to note over here that we cannot further divide this value, because this remainder 1 that we have over here, now it is less than this value 4. And this thing, when we are talking about Euclid's division lemma, we are saying this thing, it is mentioned over here. We are saying that the value of r, the remainder that we have, it lies between 0 and b, or we are saying that r is greater than equal to 0 and less than b. So the possible values of r, they are, we are saying r can be 0, it can be 1, 2, so on up to b minus 1. So these are the possible values of remainder. Now if we are looking at this division again, what we obtain from this is, what our Euclid's division lemma says, it says that we can write 117, that is equal to, it is bq plus r. It means we are talking about 4 into 29 plus 1, and clearly we have this remainder 1 that we have, it is less than 4. Now these terms we are talking about, when we are talking about this number 117, it is called the dividend. It means we are saying that the two given positive integers a and b are there. We are saying we are given two integers a and b, so this a is basically called the dividend. The number b, or this value 4, we are saying it is called the divisor. And the two numbers q and r that we have obtained, they are called quotient and remainder. And in this particular example, we have obtained the value of q is equal to 29, and the value of r we have obtained, it is equal to minus 1. So in these terms, we can write this statement. We are talking about a is equal to bq plus r. We can write it in this form, that dividend is equal to divisor into quotient plus remainder. So based upon this formula, we are going to solve certain examples. So first is, a number when divided by 73 gives 34 as quotient and 23 as remainder, and we have to find that number. So what is given to us is this value 73, it is the divisor. This value 34, we are saying it is the quotient, and the remainder we have, it is 23. Now by Euclid's division lemma, we have dividend is equal to divisor into quotient plus remainder. When we substitute these values, we are saying that the value we have, it is, the divisor we have, it is 73, the quotient is 34, and the remainder is 23, and we have to calculate the value of dividend. So using the board marks, we are saying first of all we have to multiply this 73 with 34. The answer we obtain, it is 2482, and when we add 23 to it, the final number we obtain, it is 2505. So we are saying the required number, it is 2505. Now next, we suppose that there is an arbitrary positive integer n, and we are dividing this integer by 2. We are talking about n is any integer and we are dividing it by 2. So by Euclid's division lemma, we will have two numbers, we will obtain two numbers, m and r. Those two numbers, they will be called quotient and the remainder, such that we can write n is equal to 2m plus r, and r can have the values, we are saying r is greater than equal to 0 and less than 2. It means the possible values of r, they are either r is equal to 0 or r is equal to 1. Now if we substitute these values of r in this value of n, we are saying n is equal to 2m plus r, we have either r is equal to 0 or r is equal to 1. It means the value, the possible values of n that we can have when we substitute r is equal to 0, we will have n is equal to 2m. When we substitute r is equal to 1, we will have n is equal to 2m plus 1. So what we have obtained over here is that any positive arbitrary integer, either it is of the form 2m or it is of the form 2m plus 1, where m we are saying it is some arbitrary integer. So how we can understand this situation is, suppose I am talking about any number, say it is 7. So we are saying we can write this 7 is equal to 2 into 6 plus 1. So we are writing this 7 in the form 2m plus 1, where the value of m we have, that is equal to 6. If suppose I am talking about, say, number 10, I can write this 10 is equal to 2 into 5. We are saying this is of the form 2m, where we are saying the value of m we have, it is equal to 5. So likewise we are saying that if we have any positive arbitrary integer n, then either it is of the form 2m plus 1 or it is of the form 2m. Now based upon this observation, we are going to solve a problem over here. It is, show that every positive even integer is of the form 2m. So this is the first part we have. We are saying that every positive integer is of the, every even integer is of the form 2m. So we have seen, what we have seen in this example is that if n is any arbitrary positive integer, then either n is of the form 2m or it is of the form 2m plus 1. So in the first case, if we are considering that n is of the form 2m, then clearly this number will be even. So this proves the first part of this question. Now in the second part we have to prove that every positive odd integer is of the form 2m plus 1, where m is some integer. So for the second case, we are considering the second form of n. We are saying when n is equal to 2m plus 1. So in this case, the number n that we have, it will be an odd number. So this proves our result that every even integer is of the form 2m and every odd integer is of the form 2m plus 1. Next is, show that any positive integer is of the form 3m, 3m plus 1, 3m plus 2. it is one of these three forms for some integer m. So again, suppose we are saying that n be any arbitrary positive integer. Now we require the answers in terms of 3m, 3m plus 1 and 3m plus 2. It means we are interested in the divisibility in terms of 3. Because by Euclid's division lemma, we know that we are going to write it in the form A is equal to BQ plus R. So we are over here, these coefficients of m, they are 3. So that is why we are saying that on dividing this number n by 3, we will obtain two numbers m and r. M is the quotient and r is the remainder, such that n is equal to 3m plus r. This part of answer we are getting by using the Euclid's division lemma, where we are saying that if n is divided by 3, then we can find numbers m and r such that n is equal to 3m plus r. And the condition we have on r we have is that 0 is less than equal to r is less than 3. It means there are three possible values of r. Either r is 0, or it is 1, or it is 2. Now, in the first case, when we are saying the value of r is 1, we substitute the value of r equal to 1 in this value of n. We will obtain the value of n as 3m. When we are saying remainder r is 1, it means the number will be of the form 3m plus 1. And when we are saying that the remainder we have over here, it is 2, then the number n will be of the form 3m plus 2. So we have obtained that for any positive integer n, for any arbitrary positive integer n, n is one of the forms 3m, 3m plus 1 or 3m plus 2, and this is what we have to prove. Now the next question we have is show that any positive odd integer, so we are talking over here about the odd integer, we have to prove that it is of the form 4m plus 1 or 4m plus 3. So the coefficient of m over here we have, it is 4. It means we are interested in divisibility with 4. So suppose we are saying let n be an arbitrary odd positive integer. We are considering n to be odd, and we are saying on dividing n by 4. I hope this is clear to you that why we are dividing it with 4, because the answers we require that should be in the form 4m plus 1 and 4m plus 3. That is why we are dividing this number n by 4. So by Euclid's division lemma, we are saying we will have two numbers m and r. M is the quotient and r is the remainder, such that we can write n is equal to 4m plus r, and the remainder we have, it is less than 4. It is a whole number which is less than 4. It means the possible values of r, they are either r is 0, it is 1, 2, or it is equal to 3. Now if we substitute these values of r in this value of n, so in the first case when we will substitute r is equal to 0, we will get n is equal to 4m. When we substitute r is equal to 1, we are saying the value we obtain it is 4m plus 1. When we substitute r is equal to 2, we will get it is 4m plus 2. When we substitute r is equal to 3, we will get it is 4m plus 3. So we are saying that if we divide n by 4, n can be of any one of these 4 forms. But now coming back to what we have considered, we are saying n be odd positive integer. Now look at these two numbers. We are talking about the number 4m and 4m plus 2. So clearly both these numbers, these are divisible by 2. That is, these two numbers, these are even. We are saying when we have the number 4m we can write this is equal to 2 times 2m. It means 2 divides 4m. It is even. Similarly, when we are talking about the number 4m plus 2, we can write this is 2 times 2m plus 1. So clearly we have this factor 2 over here. It means that 2 divides 4m plus 2. It means both these numbers, these are even. But what we have considered, we are saying that n be arbitrary odd positive integer. It is odd number. It means that n cannot be equal to 4m and n cannot be equal to 4m plus 2. So what values we are left now for the m? We are saying that n should be equal to 4m plus 1 or 4m plus 3. And this is what we have to prove, that if n is any arbitrary odd positive integer, then it is of the form 4m plus 1 or 4m plus 3. Now next question we have is, if n is an odd integer, then we have to show that n square minus 1 is divisible by 4. Now from our previous question, we have already obtained that every odd integer is of the form 4q plus 1 or 4q plus 3 for some integer q. This thing we have proved in our previous question. So we are talking about two cases over here. First is when n is equal to 4q plus 1, we are saying n can have two forms. Either it is of the form 4q plus 1 or it is of the form 4q plus 3. So in this first case, when we are saying n is equal to 4q plus 1, now what we have to prove is, we have to prove that n square minus 1 is divisible by 8. We have the value of n is equal to 4q plus 1. We are going to calculate the value of n square minus 1. When we substitute n is equal to 4q plus 1, we get the value in this form. It is 4q plus 1 whole square minus 1. When you open this square, you will get it is equal to 16q square plus 8q plus 1 minus 1. So this 1 and minus 1 gets cancelled, and we are left with this, the value it is 16q square plus 8q. If we write 8 common from both these terms, we are left with this q plus 2q square, and clearly from this term we can see that this term is divisible by 8. Coming to the second part, we are saying in the case 2, when n is equal to 4q plus 3, and we calculate the value of n square minus 1. The value is, we are substituting n is equal to 4q plus 3. So we get it is 4q plus 3 whole square minus 1. On solving this whole cube, we will get it is equal to 16q square plus 24q plus 9 minus 1. On solving this, we get it is 16q square plus 24q plus 8. Now again from these three terms, 16q square, 24q and 18, we can take 8 common. When we take 8 common from this first term, we are left with is 2q square. From the second term, we are left with is 3 times q. And from this third term, we are left with is 1. So how we are taking this common, we are writing over here what we can write. 16 we can write it is 8 into 2 q square plus 24 we can write it is 8 into 3 times q, and this 8 we are writing it is 8 into 1. Generally what mistake students commit over here, they write 16q square plus 24q plus 8. When they take 8 common from these terms, they write the answer in the form 2q square plus 3q, and they do not write this term plus 1 over here. They forget to write this term plus 1 over here. So you should write, if you feel some confusion at this point, you can write this 8 as 8 into 1 So that when you will take 8 common from these 3 terms, you will get the answer in the form 8 times 2q square plus 3q plus 1, and this 8 is over there. It means that this number n square minus 1, it is divisible by 8. So we have proved that any odd integer, it is either of the form 4q plus 1 or of the form 4q plus 3. And in both these cases, if n is 4q plus 1, then n square minus 1 is divisible by 8. If n is 4q plus 3, then n square minus 1 is divisible by 8. And this is what we have to prove, that if n is an odd integer, then n square minus 1 is divisible by 8.